This is physics lesson 7.02. We're going to do this one in two parts. The first one, we're going to talk about the concept of open versus closed systems. And for the second part, we're going to do a sample AP physics problem. So this handout is one I got. I found a video on YouTube, and this handout I thought was fantastic in the way that it described open versus closed systems. And so we're going to go through this in part one. Energy is, we said in the last video, a little bit nebulous. It's a little bit tough to figure out where it's at. And so what we have to do is we have to look at expressions of energy like movement. And we said that we talk about work being force operating over a distance, and that can equal the change in energy. Well, this is all dependent on what your system is. When we're talking about open versus closed systems, a closed system, by definition, the energy, I'm not taped down here, so the energy is conserved within the system. In an open system, the energy, remember E, capital E is energy, enters or leaves the system. And you might be saying, wait a minute, energy is always conserved, so how is this a possibility? Remember our diagram in the last video that had all the energy bubbles, and we had mechanical, we had thermal, we had sound. So what we're talking about is we're talking about conservation, and let me get a highlighter here, within the system. And so we're talking about whether energy is staying in the system or whether it's leaving the system. And we have to understand that a lot of this depends on how we define the system. So a closed system, by definition, the energy is conserved within the system. That means there are no external forces acting on the system. All of the forces are internal. This is another point of potential confusion. Back when we did Newton's third law, we talked about internal and external forces. So we talked about external forces as forces that are acting on an object, and internal forces are forces that are exerted by the object. Now we're talking about internal and external forces in relation to the system. So we're talking about on the system. So external forces are operating on the system. Internal forces are exerted within the system. So you have to make sure that you understand the difference between some of our previous definitions and what we're talking about now, where system is the key word. We have energy and momentum are conserved. Don't worry about momentum. We haven't gotten to that yet, but when we do, we'll come back to this handout. So two of the forces that are often conservative forces are gravity and the spring force, but we're going to see it depends on how we identify our system. So let's take an example of a ball in free fall. A ball in free fall, and we're going to ignore air resistance. So I need a free body diagram. So here's my ball. And one of the things you're going to want to do, especially early on, is you're going to want to, so there's my ground. Here's the ball. And I have the force due to gravity acting on this ball. So I've got Fg. If I make my system, so I'm going to create my system as a ball ground system. To define your system, draw a box or circle around the objects in the system. And I have my free body diagram here for my ball. So I'm going to do a dashed line. I only have one force at work because I'm ignoring air resistance, and that is within my system. So this is an internal force. And I'm going to have a closed system because all of my forces are internal. So this is a closed system. Okay, so let's look at an open system. There are outside forces acting on the system. Energy enters or leaves the system. Common, but not always, outside forces can be applied force, but almost always friction. And remember back in our energy bubbles on the last lesson, when we rubbed our hands, we saw that energy leaves in the form of sound and it leaves in the form of heat. So energy and momentum are not conserved. And again, let's add that within the system, inside the system, because they're always conserved. We're going to see later too that momentum is conserved, and we talked about the fact energy is always conserved, but they don't stay inside that mechanical energy bubble. So the energy in the system changes by the work done on the system. And this is where we had in the last video, we're going to do work in the next, in 703, but we had that work is equal to the change in energy, and we have work is equal to force times distance. So we're going to get into these equations a little bit later. Momentum is going to come much further down the road. So I want to take that same example, and I want to show you how changing our system can change the definition of it being open or closed. So let's take that ball in free fall, ignoring air resistance. And here's my ground. And I have the force of gravity on the ball. But this time, I'm not going to include the ground in my system. I'm just going to make the system my ball. So the system is the ball. So I've put a dashed line around my system. Look at what I've got going on. This force is now operating outside the system. So because I changed my definition of my system, this is now acting as an external force. I did not include the ground. So this is now an open system because all of the forces that are at work are not inside of my system. So we now have an open system. And this is doing work. This force is causing the ball to move this distance. So my motion is going this way, and it's this distance. And this is doing work on my system. So this is going to be increasing the mechanical energy of my system. It's not just, I think, let me go back up to my definition. Yeah, okay, so it could be, we could have energy in an open system. Energy can leave or enter the system. And in this case, the mechanical energy is increasing. All right, then on the second page, I can find where I put it. You have some examples. I'm going to switch sheets here. So what we have restated is that whether a system is opened or closed, see if I can focus that anymore, depends on how the system is defined. So if it's a single object, like we had the ball and we had the dashed line around the ball, we didn't include the ground. Any force acting on it will change the energy and momentum of the system. So that's what we saw in our second example. Object Earth. If the system consists of an object in the Earth, then any force other than gravity acting on its external is external and will change the energy and momentum of the system. So in this case, our first example we used was a falling ball in a ground system. And because the ground was part of the system, the force of gravity was internal and didn't change. If I put air resistance into this, and I didn't, that would be an external force, and it would change the momentum of the system. And I was going through practice problems on the AP website, and they actually have a problem, and they ask you, they take that example of a ball ground system, and they ask you if it's an open or closed system. And I just right away put closed because I've been working with these problems, and the ball and the ground, it's always a closed system. But they didn't say ignore air resistance. And what I found was it was actually an open system because air resistance was causing a change in energy. Spring object, if the system consists of an object and a spring, then any force other than the spring force acting on it is external. We're going to get some practice on the practice problem, so I'm going to wait on that. So multiple objects, we'll do more of these later. Those are there for your reference, but friction, unless the surface on which the object is sliding specifically is included in the system, friction between the object and in the surface is an external force and will decrease the energy and momentum of the system. In other words, friction always takes energy away from the system. Note, including the earth in the system does not count as including the surface on which the object is moving. And I don't know that I've ever seen an example of this. I haven't worked through all the sample problems, but I have not seen AP board define a system as a block spring. They'll say block spring earth, but I've never seen it defined as block spring earth surface. So again, you can almost, at least so far, in my experience, 99.9% of the time, friction is going to be an external force, and it will cause a change in conservation of energy within the system. We'll see energy bleed from that mechanical bubble over to thermal bubble and over to the sound bubble. All right, so that's your introduction to open-closed systems. In part 2, we're going to take an AP practice problem. We're going to look at this in a little more detail. Thanks for watching.